The next speaker is going to be Lucas, Ike, or Rocco. I'm not sure which way round the three of you want to organise the various different parts of the discussion.
Yeah, it doesn't matter to me. So I think Ike won't be presenting. I will be presenting, Rocco. So, but
yeah, I can also start. It's fine with me.
I don't know. Volunteers.
Share. I mean, I volunteer. I mean, I can just share my screen if that's okay.
Off you go.
Right. Let me share my screen. Okay, let's see. Are you able to see my screen? Does it work?
Yes.
All right, great. So let's get started. Yeah, so welcome everybody to my presentation towards a unified solution for SystemC tracing and analysis. Yeah, let me just quickly introduce myself. So my name is Lukas Jünger. I'm from a company called Machineware. I'm also co-founder and managing director of that company. And Machineware is a company that focuses on virtual prototyping, especially for RISC-V systems, but also other systems. And I have been working on simulation topics for, like 6 years now, so in different roles at GreenSox and at Synopsys. But most of my experience actually stems from my scientific background at RWTH Aachen University, where I worked on full system simulation and especially novel acceleration techniques for these simulations. And I'm active at Accellera Systems Initiative. So I'm the chair of the SystemC CCI working group, and I'm also a member of the SystemC language working group and the common practices subgroup. So what do I want to talk about today? I want to talk about SystemC tracing and trace analysis, but first I want to start to bring everybody on the same page with a short introduction to virtual platforms. I think most of you probably know everything on that slide, but I will just quickly reiterate it. So when I talk about virtual platforms today, what I mean with a virtual platform is a full system simulation. So a simulation of an entire electronic system like an SoC or an ECU. And these full system simulations or virtual platforms are traditionally used for software verification and analysis. So they can run the unmodified target software of the system that you are simulating. And since they are software and very flexible and easily changeable, they are also used for architecture exploration. The way in which this works is depicted here on the right-hand side. So you have your virtual platform and you feed it your target software, and then it executes the target software and it generates simulation data. And the simulation data can be of different forms. So it can be, for example, SystemC data. So what kind of events have been triggered, what kind of processes have been running for what amount of time, what TLM transactions happened, and so forth. But it can also be data from the models that you have inside your simulation. So as I mentioned, a virtual platform is a simulation of an entire SoC. So you have CPU models, interrupt controllers, peripheral models, accelerators, and all these kind of things in there. And they also can generate simulation data, for example, information about their performance. Or, for example, if you have cache models, you can get information about the cache utilization. But most importantly, also the behavior of the target software. And there's much more data that you can gather with a virtual platform. And actually, this data is what is most important to the user. So for the user, the virtual platform is just a tool. It should just work, and it should produce the kind of simulation data that is interesting for the user, so that the user later on can then take that data and analyze it to improve the system, for example, that he is simulating. So we are at SystemC Evolution Fika, and of course, I want to talk about how we can improve or evolve SystemC. And one of the major problems that we have right now is that there is no standard for storing simulation data. So we have a nice standard for making or for building simulations, for example, from components that you get from different vendors. So when you make your SoC, you buy IP components from different companies, and they might also give you SystemC TLM compatible simulation models that you can then combine into a virtual platform. And this virtual platform then generates data. But yeah, how this data is stored is basically up to the implementer of the virtual platform. There is some small exceptions. So there are value change dumps, which you can use to generate signal or waveforms. And but besides that, and especially for the TLM world, there is nothing in the SystemC standard that could help you to store this data in a uniform way. So what does it mean that there is no standard? Basically, the situation is depicted here on the right-hand side. So you have your more or less standard SystemC TLM simulation, and it outputs data into a non-standard database, and then some tool will visualize the result for you. However, it is very difficult if you have models from different vendors, because maybe they don't know how they can store their data into the simulation database, so you cannot see all the results. So it's a difficult situation because there is no standardized format for how you put things in this simulation database. There are some low-hanging fruits that can be, I think, addressed quite easily, and this is especially related to data from the SystemC kernel that we can easily gather and put into a simulation database, because the SystemC kernel is a part that we control. But of course, if you want to store model data like cache information or target software behavior information, then this is very specific to the model, and so aligning on a standardized format for this will be difficult. This problem is already bad in normal virtual platforms, but when you think about going to federated simulation, where you have many virtual platforms, probably even co-simulations with other tools, then this problem is even more more difficult, because you have more input sources of data, and you have to combine it in some form to analyze it, because of course in federated simulation, that's also your goal. You want to know what the system is doing, so you want to look at the simulation data. So this is the need that I see for evolving SystemC, and which is what I want to talk about today. So we should evolve SystemC to cover this as well, so that we can have a nice unified storage format and easy visualization of the results. So how can we address this? So we propose the following solution. So first of all, I think we should align on a storage format, and there we did something that is very easy. We just took an SQLite database. And then we need, of course, an idea about how we should store data in this SQLite database. And there we took a divide and conquer approach. So we first looked at the SystemC data, like TLM transactions, etc. But then also at more complex data types, for example, target software behavior traces. And we evaluated this actually in collaboration with the Institute for Communication Technologies and Embedded Systems at RWTH Aachen University, specifically with Niels Bosbach, who is also today in this call. And we came up with a solution that we call SIMDAL, the Simulation Database Abstraction Layer. And basically what SIMDAL gives you is an API that wraps databases, and it's actually agnostic to the database. So we used SQLite, but you could change it if you like. And this API offers you different trace formats. It takes care of thread safety. So you can just dump the simulation data through this API into the database. And the nice thing about this is it is completely open source. So you can go and check it out. I put the GitHub link down there. So now that we have gathered all the simulation data, of course, we have to come to visualization. So what do we do with the data that we gathered during the simulation? How can we look at it? And this is something that we are continuing right now at Machineware. So we developed a tool that can read the simulation database, and it is called Insight. And basically what it is a SystemC simulation profiler. So it tells you what's going on in your simulation from the simulation data that is stored in the database. Both of these things, SIMDAL and Insight, are completely SystemC TLM2 compatible. So you can use it in any SystemC TLM 2.0 compatible simulation that you like, and get results and see what your simulator is up to. Of course, now you might say, well, you make your life very easy. You just selected an SQLite database. Isn't that too slow? Is the performance good enough of an SQLite database? So the question of, is SQLite too slow? We can, of course, we took a look at it, and the answer is no. So SQLite works really well. So in this figure, you can see basically a graph. On the x-axis, we have the different traces that we implemented in SymDal. So for reference, we have, of course, no tracing enabled. And then we have all the other trace kinds like task switch for operating system task switches, or TLM transactions, quantum traces, the output of the simulation, and so forth. And on the y-axis, we have the elapsed simulation time. So lower is better. In this evaluation, we executed 2 seconds of a Linux boot on a virtual platform called AVP64. That is an open source ARM virtual platform that you can use to run Linux or even hypervisors. And we basically analyzed the overhead of gathering the simulation data. And I mentioned that SymDal is agnostic of the underlying database, so we compared 2 different things. So we took CSV files, which is just basically a text file, and we took the SQLite database. And you can see that overall the overhead of the tracing is really not very high. There are some complex traces, for example, the call stack trace, which samples the CPU call stack during simulation and shows you what the CPU is doing to generate a flame graph of the program that is running on your simulation. This is a complex trace, and there we can see a clear performance benefit of using SQLite. So it's much faster than using a CSV file. But overall, the overhead is really low. So you can see it's maybe 6 seconds slower, so 20% in the worst case. So that's not too bad. That's basically what I wanted to show you today. So let me summarize. So what is the takeaway of this presentation? So basically, we should align on a trace file format for storing simulation data into a database. We tried it with SQLite. It works really well. It's also very easy to implement, and there's an open source implementation that can serve as a starting point for discussion. If you would like to learn more, of course, follow us on LinkedIn, or if you are more a code person, you can also star us on GitHub. You can, of course, also write me an email, and I encourage you all to join this conversation in Accellera and get involved. So thank you very much.
Thank you indeed, Lucas. Either my tummy is rumbling or that's thunder in the background. Sorry about that. Were there any questions on Lucas's presentation? If not, we can move on to Rocco and then take questions at the end.
I have just a quick one.
Sure.
And for Lucas, obviously, and I didn't understand if the in S site, if that is okay. This is something that yourself and your company are developing, but is that open source as well, or is just an in-house tool at the moment?
So so Insight is an in-house tool that we are developing at Machineware, but we are relying on the open source database format.
Okay. Thank you.
Yeah, I have another question here, which is basically, is this standardizing at the right point? Because I would expect the first thing that needs standardization is essentially the API you add to your models to export the data, based on my own experience in doing similar things. I mean, the format is kind of a tertiary concern in my experience. The hard part is actually getting the data collectors into the models in an interchangeable way, which honestly, in a way, goes towards the CCI working group, right?
I would probably divide this into 2 parts. So, I mean, first of all, I think for the data that is only related to the SystemC kernel, it's not really required, because we can just add this data collection to the SystemC kernel because we control it. For the models, it's a bit more tricky because, I mean, if you control all the models, okay, that's great. I mean, for example, in our modeling library, VCML, we could add the feature to dump the data to each model, and we control it, and that's fine. But I think if you have a simulation that consists of models of many different vendors, it will be very hard to convince them to to follow this basically. By providing the SIMDAL API, we actually make it quite easy, because the SIMDAL API basically tells you how you store data into the database, and it takes care of thread safety. So basically what you have to do as a model author, you basically include the SIMDAL header file, and then you just write out the data whenever you want, because you don't have to worry about the thread safety, nothing. So SIMDAL will take care of all of this for you. So I think I would claim it's kind of a mix. Of course, it would be even better if we convince everybody to on how they dump the simulation data from the models. But we at least partially solving this by providing an API that takes that defines the trace data that you are capturing, because that you have to do anyways if you do it in the model or in the database wrapper.
And so the rephrased, you're really saying that the SIMDAL API would be, in a way, it's kind of the same level as the CCI APIs, in the sense that you would have your custom private implementation of data collection for the models you write using your own frameworks. I mean, if you're a Synopsys or Cadence or Machine or whoever, but then in the back end, once the data is collected, you would have a common kind of output mechanism in the form of SIMDAL.
Right. So the idea is that I basically can visualize the data that comes basically from any model, because we have agreed how we store the data. So that when I open my viewer that comes from any company, it can read the trace data basically of any model. So that we don't have basically, yeah, so that because else you will have dark spots in your analysis, right? So if you include models into your simulation that don't adhere to a predefined data collection mechanism, you cannot see the data from these models in the visualization tool. And so that's kind of the problem we are trying to solve here.